My name is Marcos Rubinstein. I am with the University of Applied Sciences and Arts, Western Switzerland, and the title of this presentation is Introduction to Lightning Location. The outline of the presentation is the following. We're going to be looking at what is it that we want to locate first, very briefly, and then we're going to dive into three methods that are the main methods used nowadays. Basically, actually, the first two are the main methods used in commercial systems for location of lightning, and the last one is an experimental method at this time. So what is that we mean when we say that we want to locate lightning? If you look at this picture, you see one big bolt of lightning which measures kilometers. So what is it that we want to locate? Do we want to locate every point along the channel so that we can reconstruct it? We want to locate the cloud? Do we want to locate the discharges within the cloud? We want to locate the strike point at the ground? And in reality, what we're going to be looking at, even though all of those are possibilities and they can be interesting for research purposes, for example, what we're going to be looking at is how to locate the point of impact of the lightning at the ground. So what we see here is a cloud, and we see a skyline here of some sort, and the lightning starts from the cloud. We're talking about cloud to ground lightning and downward cloud to ground lightning. There's also upward, but the most common type of ground lightning is downward lightning. What you see here is this discharge that branches massively as it goes down, and it is actually in light yellow because it is a faint discharge at the beginning, and it turns actually very luminous as soon as it reaches the ground. What happens is that when you get to the ground, there is a short circuit between the potential that was brought from the cloud to the ground and the potential of the ground. At that point that I just showed here, you have a big current of the order of some maybe 30 kiloamps that's going to be moving up very fast at 2/3, maybe 1/3 to 2/3 the speed of light, and it will light up the channel. But what's interesting is that since for practical purposes, we are interested actually in finding the location of that big pulse, this is a good thing, because this big pulse is going to be radiating electromagnetic waves, and we can measure those waves far away and use those waves to locate the lightning using the methods that I'm going to talk about in a minute. One more thing before we look at the methods is that this is actually the first stage in a cloud to ground lightning. In fact, after some point where you have no current, you have a second discharge. This time usually doesn't have any branching, and when it reaches the ground, again you have a short circuit that produces again a big current. This time it's going to be on average like 10 kiloamps or so, and there will be this current going up again at speeds comparable to the speed of light. Now let's look at the first method, which is called magnetic direction finding. So to do that, we're going to take the same picture that we used just now, and we are going to idealize this skyline. We're going to be making this flat, and let's look at it in perspective a little bit. So we have this return stroke. I didn't show the downward discharge, only the upward discharge that is faster, the one that produced this pulse here at the bottom. What happens is that this pulse at the bottom will produce a radiation that will radiate outward radially, and it will produce electric and magnetic fields. What's interesting here is that the magnetic field is actually perpendicular to the direction of propagation. So basically, because it is perpendicular, there's 90 degrees there, you can actually find the direction to the lightning just by drawing a line that is perpendicular to the magnetic field, if we manage to measure this magnetic field. Of course, you don't know if the lightning is coming from this end or from that end, so it could be any place along this line. We are assuming here that we are only measuring the magnetic field, because if we measured the electric field, we would know by the pointing vector that the actual lightning was coming from here, or the radiation was coming from this direction. What we have here is a couple of magnetic field sensors capable of measuring two components, meaning the whole vector of the horizontal magnetic field. So when you have a lightning that happens someplace, at some point you're going to be measuring the magnetic field that arrives at this sensor. We could do the same thing at the other sensor, and now, as we said before, just by drawing a line that is perpendicular to the direction of the magnetic field that was measured at that sensor, and that actually goes through the point where the magnetic field was measured, and by doing the same thing at the other sensor, then you have an intersection point here, which is the location of the lightning. In practice, you may have some problems measuring accurately the magnetic field, and if the two sensors, for example, are in line with the strike point, then you won't be able to find it, but those you can solve by using more sensor locations. Let's look at the way the magnetic field is measured. Let's start with the magnetic field vector here. It's actually B. I'm calling it magnetic field, but you could probably better call it magnetic flux density. Let's draw this field now pointing into this light, and we are going to take now a loop. This is a loop made of a conducting material, and now let's assume that we have a wave coming in, and that this magnetic field that is again pointing more or less into the slide will produce some magnetic flux through the loop. And as you know, the magnetic flux, rather the derivative of the magnetic flux with respect to time, will produce a voltage across the ends of this loop. This is actually the electromotive force that is produced. Because we have a field whose wavelength is longer, much longer than the size of the loop that we're going to be using, we can perform this integral in an easy way, because we just need to multiply the B field by the area of the loop, which is assumed to be A here, and we see here that we are getting actually a component of the magnetic field, because if the magnetic field is exactly perpendicular to the loop, then this cosine will be 1, but if it is not, then there's going to be just one component that's going to be creating the flux, and we're actually measuring one component of the field. The field can be calculated from that equation by integrating with respect to time. In any case, the fact that we can find the magnetic field, we can find one component of the magnetic field, allows us to find actually the full vector by using two magnetic loops that are perpendicular one to each other. Here you see practical examples of these two loops. These are called cross loop antennas, and they will measure actually two components of the magnetic field. This is courtesy of the EPFL EMC lab. What you see here, just for completeness, this is used actually for other methods. It is a flat plate antenna, which is typically used for research purposes to measure the vertical electric field from lightning. You can also use just a whip antenna to do that, or some other type of antenna. Let's now look at the second method, called difference in time of arrival, or also called time of arrival. So this is a time of arrival technique, TOA, or as I said, difference in time of arrival. So this is based on hyperbola. Actually, look at the hyperbola just to remind you what it is. So you have a hyperbolic branch here on the left and one on the right, and you have two focal points, F1 and F2. If you have any point in one of the branches, the characteristic basically of the hyperbola is that if you have the distances to each one of the focal points, which we can call V1 and V2, a hyperbola is defined as the set of points whose distances to two fixed focal points, F1 and F2 in this case, have a constant difference. So if the difference between D1 and D2 is constant, then the point is going to be someplace here on this branch or on this branch, depending on the sign of that difference. How is this used to locate lightning? So we can see here, we have a top view here of the terrain, and we have two sensors that are placed at two different geographical locations, and in this case we place them in the same arrangement that we used in the previous slide with the focal points. And then we have a lightning strike that happens here at time t0. So there will be a wave out radially from that lightning strike location that will reach sensor 1 at some point. So when did it reach? If the distance is d1, it reached at a time that is equal to t0, the time at which the lightning struck, plus the time that it takes to propagate from that point to that sensor, which is d1 divided by c. And of course continue now and see that the wave will reach at another time at sensor 2, and by the same method we used before, we can just calculate the time of arrival at that sensor. So having those two times of arrival, we are going to get rid of those circles now and just write the difference in time of arrival, which is the basis for the whole method. So that difference is only the difference between one of these times and the other. So we subtracted actually t2 minus t1 here. And we see that the result is actually proportional to that difference in the distances, which is basically the definition of the hyperbola. You just multiply by c. We see that by using just the time difference of arrival, multiplying it by c, the speed of light, we have the difference between the two distances to the two sensors. This tells us that this point, even though we only have the time difference up to now, but we know that this point is someplace along this hyperbolic branch. And we have the other hyperbolic branch, but we can choose one or the other by the sign of the difference in time of arrival. Now let's see how to apply this for lightning. We have one sensor here, sensor 2, and we have a strike point here, and as we saw previously, this actually defines two hyperbolic branches, of which one can be selected. If we add another sensor, sensor 3, we have another pair of hyperbolic branches. We can select the appropriate one, and we can see that we have one strike point here, and that the point is actually the intersection between the two hyperbolas. So this is a way we could find, using difference in time of arrival, the location of the light. Look at this. We have one more intersection point. So to remove this ambiguity, we can use different methods, and one of them, typically what is used, is to use more than 3 sensors. If you have a fourth sensor, then you can locate, basically you can locate the actual lightning. Let's go to the last method. The last method is electromagnetic time reversal, and this is, as I said, in experimental methods. There are no systems that use this method yet, but the theory and some even experiments have shown that this method has a lot of promise, and that it can give you a much higher not only location accuracy but even detection efficiency for these systems. It works based on what's called the time reversal invariance of many laws of physics. So this is the property of some laws of physics to remain invariant under the T-symmetry transformation, and this is the case for Maxwell's equations in lossless media, but it can be used also in media that are not lossless. Actually, this method based on what's called time reversal invariance in the soft sense. I'm not going to go into the details of the theory here, but I will show you that there is a book that you can get at the library, and then you can learn a little more about this. Or there's many publications actually in the literature nowadays. So this is the way it works. You have a lightning that strikes, that's a return stroke, and you have 4 sensors. So the sensors actually will record the pulses that we have been talking about in this talk, and what they will do is that they will take these waveforms and they will time reverse it, meaning they will flip them in time. This is what I'm going to show here. They're going to be flipped in time. Basically, the last in, first out. They're going to be propagated back into the medium. This is usually done by simulation. And what happens is that when you simulate, you realize that these waves actually will have maximum constructive interference at the point of impact. So this is the basics of the method. I'm not giving you many details here because we don't have a lot of time, but you can use, as I said, the internet to look for this, or you can also take this book out of the library if you want, which is a book that was edited by myself and the two colleagues whose names I'm not going to read now because I'm using this subtitles that is automatic, and it usually gives strange spellings, but you can read them here. So this is the end of this introduction to lightning location.